vision, the microsaccades, everything. And it's also applied to EEGs. The problem with it is, if you have, well, I don't want to go into too much detail, but let me give you an example of where it becomes critical. If you take EEG data from the caps, and say you take the occipital lobes, one channel EEG data, and you do this diffusion entropy analysis, so you find the probability density for the amplitude of the EEG, how it changes over time, get the entropy. What you find is S of t versus log of t. If this is a simple scaling process, remember I wrote down that S of t goes like a constant plus delta log t, if it's a simple scaling process. In general, what you have is this is lambda of sigma of t. And that comes, say if you have a Gaussian distribution, you have e to the minus x squared over 2 sigma squared of t, 1 over the square root of 4 pi sigma of t. This is the Gaussian distribution with a variance that's time dependent. So what you'll get from this distribution up to an overall factor of 2 is log of sigma. Right? And remember I showed in one of the plots that I had, when you have this the dissipation in the system, that the variance goes like 1 minus e to the minus 2 lambda t over 2 lambda, right? When you look at EEG data, what you find is something that looks like this. From here, what you're seeing is a growth up to a saturation level from here. And if you look at this oscillation, which damps, this has an oscillation of an alpha rhythm. And so it becomes, one way you interpret this is you're looking at an EEG signal, and the EEG signal is going to be one that has a feedback parameter lambda that's negative for controlling the system, so that the oscillations never get too large. But you also have information that's being transmitted. This is people that are sitting, eyes closed, resting, in which alpha rhythm is dominating, and you see the alpha rhythm. So you can actually construct a representation which predicts this very well. The point is this region. And what the detrended fluctuation analysis says, this is a quantity versus the log of time, and what you have here is essentially a straight line. And so if you looked at the data and you were looking at this early time behavior, what you would say, oh, the data scales. And then you would interpret what this scaling parameter meant. But the point is, the data doesn't scale. The data saturates. And you're only looking at an early time on what happens to this much more complicated signal. And so this is sort of true generally in the community, and it's again, I say cautionary a lot. It's a cautionary note of taking a procedure that you don't completely understand and applying it to your data and then interpreting what the result is. That you have to be, when you're applying these procedures, you have to be more scrupulous than the people that invented the procedures in order to really rely on how you're going to interpret the output.
Okay, thank you. And we will digest this one more in the coming years, maybe. Okay, maybe in the coming months. So, but I want to indicate I'm a control dynamics control person. When you face a complex a system of high complexity, so there are a need about how to measure the complexity and how to regulate the complexity. Say, for example, oh yeah, I see this society is too chaotic. I want to regulate it so that I can reduce the complexity and make sense of the life much easier. So that kind of a bigger closed-loop thinking, like a sensor and actuator type thinking, closed-loop thinking, I didn't see in any literature. I don't know how to approach it. And say, for example, like network science and how to giving a network and what kind of thing you really can do to regulate the complexity related to this network. Is there any existing work on it?
There have been, well, this is an example. It's not to control or regulate the system, you first have to understand the dynamics of the system.
Right.
You have to have a model. And this is the first actual mechanistic model of sort of what's happening in the brain.
Okay.
Dynamically. That doesn't involve like neural networks.
Mm-hmm.
That strategy for adopting it is strictly in terms of the dynamics. Well, you'd like one for the economy.
Regulate the economy. Yeah,
One that
very high level.
Yeah, you'd like to be able to just to make a reliable recommendation that either these things that people are doing are going to succeed or are going to fail, rather than saying, well, I've got to do something, so let's do this, which is what they're doing now. They're doing this social experiment that involves billions of dollars, and in a number of years we'll find out whether the experiment was successful.
I think President Obama is doing this quantification and regulation problem.
Well, yeah, that's his job.
Yeah, he's doing this, I guess.
He's supposed to make society stable, and he's only as good as his advisors. And his advisors, and the economic advisors, don't understand, they may understand a stable economic system, but when it begins to become unstable, how to restabilize it, I don't think that they have a clue any more than anybody else does.
Yeah, if President Obama used some faulty sensors to tell the wrong story about this complex, then he regulates and he can blow up the system, it's possible.
That's a possible outcome.
So I think we are really behind the schedule. This one, we leave this one to the Adams Park, and we keep discussing Kansas too. And that's okay. I don't want to do that. And currently, I feel like we need a demo, and so that's why I build a demonstration corner for fractional control. Whenever we got a visitor, I will show them and fractional control in action. So we do have a few systems, and let's stay here for 5 more minutes, and then you can go around and, while preparing to leave. So in 10 minutes, we'll definitely leave this building and go to the field. Okay? All right. Thank you very much for the full day.